Okay, well, today we're going to finish up our new material for now with Gibbs Free Energy related to equilibrium. And this is actually from chapter 20 in our book, where we did the beginning of chapter 20 back when we did heat, enthalpy, and we added in entropy and Gibbs Free Energy. So way back when we did chapter 6, we also did some of chapter 20 with entropy and Gibbs Free Energy. And if you remember, Gibbs Free Energy, delta G, is a measure of spontaneity. So we had two different equations back then to calculate delta G. We could do this equation, which is delta G equals delta H minus T delta S. And then we also had the equation where we could look up the delta G values, the G's of formation in the back, and did products minus reactants. So in both cases, delta G, when it comes out to be negative, that means the reaction is spontaneous. When it is 0, that means the reaction is at equilibrium. And when delta G comes out to be positive, it means the reaction is not spontaneous in the forward direction, but it would be spontaneous in the reverse direction. So we're going to just very briefly review delta G a little bit, and then we're going to apply that to when we're at non-standard conditions and then at equilibrium. So let's keep going here. So sample problem with that equation, with the delta G equals delta H minus T delta S equation, determine whether the following reaction is spontaneous at 25 degrees Celsius if delta H is negative 393.5 kilojoules and delta S is 3 joules per Kelvin mole. And there's our equation that carbon plus oxygen makes CO2 gas. And remember, with this equation and with all equations, you always have to make sure your units match. Delta H was given in kilojoules, delta S was given in joules, so we're dividing by 1,000 to put our delta S into kilojoules. And then it's kilojoules per Kelvin mole, and temperature has to be in Kelvin to match that. So plugging that in, negative 393.5 minus 298 times 0.003 kilojoules per Kelvin mole equals negative 394.4 kilojoules. Now, actually, I should have a little degree sign on this delta G because I am using standard delta S and delta G values so that my delta G value would be under standard conditions also in this case. And when it's under standard conditions, that means it's 25 degrees Celsius, and if they're gases, the pressure is 1 atmosphere. So this is also called G naught, delta G naught, delta H naught, delta S naught. That means it's at standard conditions. Okay, so our delta G value came out to be negative. So yes, this reaction is spontaneous at 25 degrees Celsius. It doesn't say anything about how long it takes, how fast the reaction goes. It just says, yes, it is spontaneous. So again, the standard free energy is that not. And the energies of formation are back in Appendix B. The other way we can calculate delta G is by doing products minus reactants with the delta G's of formation. But anytime you see that degree sign, it means standard state. So it's either a pure solid, a pure liquid, or a gas. And if it's a gas, it's at 1 atmosphere. Or if it's a solution, it's 1 molar concentration. That is what standard means. And also the temperature is at 298 Kelvin. And then for elements that are naturally occurring, the standard delta G value is 0. And again, the delta G value tells us whether or not the reaction will spontaneously occur to produce either more reactants. If it comes out to be positive, it means it's spontaneous in the reverse direction. Or if it is negative, less than 0, then it means it will spontaneously occur to produce more products. And our other equation to calculate Gibbs free energy is this sum of the SUM, sum of the G of formation of the products minus the sum of the G's of formation of the reactants, which we can look up those values. And then the values on the chart are always for 1 mole. So this N and this M are representing the moles in the balanced equation. So we have to multiply, if it's 2 moles of water, we have to multiply it by 2, the geoformation value. Okay, so products minus reactants, multiplying by any coefficients to get delta G is the other way. So whichever information is given, if we're given the delta H and the delta S, we'll use the other equation. If we're given the geoformation values, we'll use this equation to calculate delta G at standard conditions. But sometimes we will need to calculate delta G at non-standard conditions. In that case, this is the equation, delta G equals delta G equals delta G naught plus RT natural log of Q. So if you remember, Q is the reaction quotient. That is products over reactants, just like capital K is, the equilibrium constant. But this is with the initial pressures or concentration. Initial pressures or concentrations. So products over reactants, initial not at equilibrium, that's what Q is. And R in this equation is our joule R because delta G is in kilojoules. So we need to divide the 8.314 joules by 1,000 to put that into kilojoules so that our units match. Temperature must be in Kelvin. So one method for synthesizing methanol involves reacting carbon monoxide and hydrogen gas. So here's the equation. Carbon dioxide gas, 1 mole of it plus 2 moles of H2 gives us 1 mole of methanol. To write what the Q expression is for this, products over reactants, but remember pure liquids and pure solids don't have a concentration, so it's just a 1 for the product. And then the amount of CO2, if it's a concentration, it will be in brackets. If it's a pressure, we usually just write P. There's just 1 mole of that. But then the hydrogen is squared. H2 amount is squared because there's 2 moles of hydrogen in the balanced equation. So for this problem, it says calculate delta G at 25 degrees Celsius for the reaction when the carbon monoxide gas at 5 atmospheres and hydrogen gas at 3 atmospheres are reacted. So the delta G does not have the little degree sign on it because the pressures aren't at 1 atmosphere. So that means, going back up to this equation, we need the delta G naught, and then this is like a correction to it, to calculate delta G at non-standard conditions. So we either have to be given this delta G naught or we have to calculate it. So we weren't given that in this problem. So I looked up the values for these in the back in the appendix on the chart, Appendix B in our book, to calculate the delta G. So the delta G of formation for liquid methanol is negative 166.2. The value for hydrogen, since it's naturally occurring, is 0. And the value for carbon monoxide gas is negative 137 kilojoules. So I do products minus reactants to calculate delta G. So the methanol value goes first, minus the carbon monoxide value, which is negative, and I come up with negative 29.2 kilojoules for my delta G naught. Okay, so at standard conditions, that's the delta G value. So for that equation, I also need to calculate Q. I already wrote the Q expression. I just need to plug in the values here. So the carbon monoxide is 5 atmospheres and the hydrogen gas is 3 atmospheres, but the hydrogen gas is squared. So it's 1 over 3 squared times 5, which is 1 over 45, which is 0.0222. And now I just can plug those values into this equation. So I just calculated the delta G naught. I'm going to plug in R. I'm going to plug in the temperature in Kelvin, and I'm going to plug in Q. And so when I do that, let's go pen here. Let's get rid of this screen. I end up with a value of negative 38.46 kilojoules. So the non-standard G came out to be a little bit more negative than the standard G in this case. And if we look, the reactants, instead of being at 1 atmosphere, which is what they would be at standard conditions, it's higher. So 5 atmospheres and 3 atmospheres. So that made it a more negative value. So it's more spontaneous when those pressures are higher. Okay, so that's calculating delta G at non-standard conditions. Okay, if I want to calculate delta G at equilibrium, delta G equals 0. So this would, putting in a 0 here for it and making this a K, I come up with this equation that relates delta G naught to K. So at equilibrium, I won't have to worry about this delta G value anymore. It'll just be delta G naught plus RT natural log of N equals 0. So subtracting the minus RT natural log of K to the other side, I get delta G naught equals minus RT natural log of K. So this is a very useful equation. This equation allows us to calculate delta G when we have K or K from delta G. So we just spent quite a bit of time calculating all the different kinds of K, whether it's Ka, Kb, Ksp, Keq, all of those. It doesn't matter what kind of equilibrium constant it is, Ksp. All of those could be plugged in here and we could calculate G from that. So this is a great equation to relate delta G to K. And what we'll see here is if delta G is negative, then the natural log of K must be positive, plugging in mathematically. If this is negative, then this is negative. So that means R is always positive. Temperature in Kelvin is always positive. So that would mean that the natural log of K would have to be positive in order for delta G to be negative overall. And that means if the natural log of K is positive, that means the equilibrium constant is greater than 1. The more negative the delta G, the larger the equilibrium constant. And that makes sense, remember, because K is products over reactants. So if we have a lot of products, it means the reaction's going in the forward direction. And then that's what it means to have a negative delta G. It means that the reaction is spontaneous going in the forward direction. Okay, so, but that's a important relationship. Also, sometimes there's questions or you need to just relate delta G to K without actually calculating. And you'll always know that if K is large, then delta G is very negative or vice versa. So there's a relationship there. If delta G naught is 0, then K will be equal to 1. So if the delta G value is 0, it's at equilibrium. The product's concentration equals the reactant's concentration, so that the K is equal to 1. If delta G is positive, then that means the K value is less than 1, and that means the reactants are favored. Okay, so anytime delta G is negative, K is going to be larger than 1. It's spontaneous, products are favored. Anytime delta G is 0, then K is going to be equal to 1 because it's at equilibrium and the products equal the reactants. And then if delta G is positive, K is less than 1. That means there's more reactants at equilibrium. Okay, so remember those relationships. Okay, so doing a problem with the equation relating delta G to K. Let's go back to this for a minute. we also sometimes want to rearrange that equation. If we're solving for K when we have delta G, we need to get rid of that natural log. So that's where we take e to the, so K, just rearranging this equation up here, okay, taking the solving for K from delta G, it will be K equals delta e to the negative delta G over RT. And just always watch your units. Delta G is almost always in kilojoules, so that means the R needs to be in kilojoules, and then the temperature has to be in Kelvin. Okay, whether you're using it in this form or the above form. Okay, so K equals E to the negative delta G over RT, or delta G equals minus RT natural log of K. Those are the two equations, the two forms of the same equation, depending on what you need to solve for. Okay, so the other problem that I want to look at, this one is right from your book, actually. It says the oxidation of 2SO2 plus O2 gas makes 2SO3 is too slow to be useful in the manufacture of sulfuric acid. To overcome this low rate, the process is conducted at an elevated temperature. Okay, so it says calculate K at 298 Kelvin and at 973 Kelvin. And then remember, when temperature changes, the delta G value would be different. And same thing if it's the delta H or whatever temperature, they're all affected by temperature. So we're given the delta G naught value at 298 Kelvin, and we're given it at 973 Kelvin. So we can just plug those values in, plug in R, plug in temperature, and calculate K. So we're going to use this form of that equation, plugging in our delta G, our R, and our temperature in Kelvin. And we come up with, at 298, the K is huge, 6.62 times 10 to the 24th, versus at the high temperature, K is much, 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 much smaller, 4.47. Okay, so this lower temperature gives us more products favored than at the higher temperature. So raising the temperature is not going to be enough. They would have to use a catalyst or something to make this go faster. Okay, so that's part A, just calculating K at those two temperatures. Okay. Part B of the equation then says, in experiments to determine the effect of temperature on reaction spontaneity, two sealed containers are filled with 0.5 atmospheres of SO2, 0.01 atmospheres of O2, and 0.1 atmospheres of SO3, and kept at 25 degrees and 700 degrees, which again, that's our 298 and our 973 Kelvin. So I'm not really sure why they went to Celsius when originally they were in Kelvin, but we need to put those back in Kelvin. So in which direction, if any, will the reaction proceed to reach equilibrium at each temperature? So now these are at non-standard conditions, these different pressures. So we need, and it's not at equilibrium yet. So we have to calculate Q, and then we're going to compare that to the Ks. And remember, if Q is too small, if it's smaller than K, it means the reaction is going to go to make more products. If Q is too large, it means we have too many products. So it means that it will go the other way. It will go in the reverse direction to produce more reactants. So comparing Q to K is how we know if the reaction is going to go in the forward or reverse direction to reach equilibrium. So plugging in those values for Q, we have 0.1, and there's, again, it's products over reactants. So there's 2 moles of SO3, and the SO3 value is 0.1. So 0.1 squared on top. And then the SO2 value is 0.5, and there's also 2 of those, so it's also squared. And then the O2 value is there's just 1 mole of that, so it's just 0.01. So plugging in 0.1 squared over 0.5 squared times 0.01, we get a value of 4 for Q. So comparing Q to K at the 298 that we just calculated, which is 25 degrees Celsius, K is way larger than Q, so it's definitely going to go in the forward direction. And then the K at 973 Kelvin, or 700 degrees Celsius, is 4.47. It's still a little bigger than Q, so in both cases, the reaction will go to the right to produce more product. And then the third part of this problem says calculate delta G for the system in part B at each temperature. So now, again, it was non-standard conditions. So we use this equation where we plug in the Q that we calculated to solve for delta G at these non-standard conditions. So at 298, we plug in the delta G naught, which was given, and we plug in R in kilojoules, temperature of 298, and the Q we calculated to be 4, so we take the natural log of 4. So plugging that in, we see that the delta G at non-standard conditions comes out to be negative 138.2 at the 25 degrees, or the 298 Kelvin. And then we calculate it with the higher temperature, 973 Kelvin, or 700 degrees Celsius. Again, plugging in the delta G that we have, plugging in R, temperature, and Q, and we come up with negative 0.9 kilojoules per mole. So this one is barely spontaneous at these high temperatures, whereas this one is still spontaneous at the negative. So the key is always watch units. These two equations are actually given on the equation sheet. So you will have that for the AP test and for my test. And just always watch units. Sometimes they might throw in a thing where the delta G is given in calories, for instance, and you have to use R, and R is in joules. So you would need to convert your calories to joules. So remember, 1 calorie is 4.184 joules. But always, always, always watch units for all of these problems, and you should be fine.